In this batch of videos, I'm going to spend some time talking about membrane potentials. This is a fundamental concept in neuroscience. It's one of the most time-consuming and conceptually difficult concepts to understand. We'll work through it in a series of videos. Rather than doing it all in one, I've broken it down into small pieces. Hopefully this will help. First, I'm going to talk about some basic definitions, some basic terms you need to know in this video on gradients and potentials. After that, I'll talk about the resting membrane potential, followed up by the longest video, which will be on the action potential, and then I'll finish up with propagation of the action potential. As I said in this video, I'm going to go over some basic concepts with you. These will lay the foundation, hopefully make the other videos easier for you to understand. After you watch this video, I want you to be able to explain the basic structure and properties of the cell membrane. Need you to be able to explain what a gradient is and what an electrical potential is. You need to understand and explain the cell membrane's contribution to establishing and maintaining electrical potentials. Two forces that we're going to talk about, force of diffusion and the electrostatic force. I'm going to start out refreshing your memory about the cell membrane. So the cell membrane, the plasma membrane, or for this lecture, whenever you hear me just say the membrane, this is what I'm talking about. It's a phospholipid bilayer. So phospholipid bilayer. This basically means it's a fat sandwich. So we got fat in here, and then we're going to have phosphate groups here. So you can think of this kind of as the bread. We got some fat in the middle, and then more bread. This covers the entire cell. Okay, so the entire cell has a cell membrane around it. It's basically going to keep some stuff in and some stuff out. It separates the inside from the outside. Everything outside is called the extracellular fluid. Everything inside equals intracellular. Okay, so extracellular, intracellular. Now, as you probably heard, 70% of your body is water. This water is everywhere, basically. So we're going to have fluid, extracellular fluid, and intracellular fluid. Both of those are water-based, but they contain different concentrations of substances. And we're going to go through and talk about those. One of the properties of the cell membrane is it's semi-permeable. So permeable means stuff can go through it. Semi means partially. Okay, so some things can go through this, other things can't. If you don't remember what can pass through, go back to the unit on the blood-brain barrier. Basically, things like gases, so CO2, oxygen can pass right through. Anything that can dissolve in fat, anything that's lipid soluble. Your opioids are like this. So heroin passes through because it can dissolve in lipid. So if I'm a fat-soluble molecule, I come along, I can just kind of dissolve my way through it and move right into the cell. Other things like charged particles or water can't pass through it. Okay, so the cell membrane is going to let a couple things through, but most things can't, not on their own. If we want to move things in and out through the cell membrane, the only way we can do it is through big protein molecules. Okay? And these are basically tunnels through the membrane. I'm going to call those channels. So anytime I'm talking about a channel, this is what I'm talking about. It's a large protein that provides a path through the cell membrane. Now, there's a lot of different states that channels can be in. They can be wide open, they can be partially open, they can be closed. If a channel's closed, obviously nothing can pass through. If the channel's wide open, things can pass through quickly. If they're open a little bit, things can pass through slowly. There's one channel that is very important. It's called an aquaporin. Okay, aqua has to do with water. Porin has to do with a hole, a pore. Okay, so this is basically a water tunnel. These are all over the cell, everywhere. They're always open. So water can't pass through the membrane itself, but there's tons of aquaporins all over the cell. That means water can freely move in and out. So I do want you to know what aquaporins are, but it's an important concept. Okay, so even though the water can't move through the membrane itself, because there's channels, it can move in and out. So it's going to turn out that some of the difference between what's outside and inside the cell has to do with these channels. Now, channels are different than transporters. We'll talk about those later. I mentioned two forces. There's a force of diffusion. This is going to basically be the force that drives molecules from a high concentration to a low concentration. Okay, so you know, for example, if someone has too much cologne on, right? That person walks in, the smell is right with them. If you're right next to them, it's going to go from their skin where they have the excess cologne, and it's going to diffuse. It's going to move down its concentration gradient and spread throughout the room. Essentially, and again, I'm anthropomorphizing here, but molecules don't have free will, obviously. But the energy, the vibration of the molecules is going to give them energy to move. And they're going to tend to move from where there's a lot of them to where there's less of them. The greater the concentration difference, the stronger the force of diffusion. Okay, so again, just the force driving things from high concentration to low concentration. There's also an electrostatic pressure. For this, if there's a separation of charge, opposite charges are going to want to move toward one another. Same charges are going to want to move away from each other. Okay, so you're fairly familiar with this. So if I have a bunch of positive charges, a force, the electrostatic pressure, is going to drive these toward each other. Likewise, if I have positive ions right near each other, these are going to repel each other. Okay, so that's called the electrostatic pressure. These two are separate forces. I want you to think about them separately. Okay. Now, equilibrium is an important concept. It applies in many, many different situations. It's kind of a general term. Essentially, equilibrium is reached when all the forces are balanced. So let's say I have a high concentration of substance here, and over here I have a low concentration of the substance. You know the force of diffusion is going to drive these molecules toward the lower concentration. How long are they going to go? Well, they're going to keep moving until the concentration in the two places is equal. Okay, so when the concentration's equal, now the net movement this way is the same as the net movement that way, and the concentrations won't change anymore. The same is going to be true with charge. Charges will move until there's an even distribution of charges. Okay. When we talk about equilibrium, we're going to basically lump all these forces together. I'll explain what this means a little bit more in a minute. But equilibrium is at the point in which there's no net movement into or out of the neuron of that substance anymore. Now, an electrical potential is a little bit different, obviously. A potential is charge separated in space. So if I've got something like this, there's no separation of the charges in space. There's overlap here of them. So here we'd have no potential. But if you think about something like a battery works because there's a separation of charge, and they're going to want to move toward one another, this electrostatic pressure. When you put this in an electronic device, for example, and you complete the circuit and allow these things to move, right, the electrostatic force is going to have these move toward each other. Okay. Now, that separation of charge is measured in volts. Okay, so in the real world, we measure it in volts. So you got 1.5 volt batteries or 9 volt batteries. There's a lot of separation of charge. It's called a potential because that separation of charge is going to allow me to do work. So essentially in this, how much work can we do when we put a battery into a device? It depends on the size of the battery. The bigger the battery, the more work it can do, obviously. Now, when we're talking about neuroscience, we're talking about really small separations of charge, very small potentials. So here we're talking about millivolts, very small amounts. As I said, electrical potentials are important because they represent the capacity to do work. We can take advantage of that electrostatic force. So electrical potential, as I said, is just a separation of charge. These is a general term. So there's many examples of electrical potentials. The one you're most familiar with probably is the battery. Now, we can get a little more specific. Instead of talking about a potential in general, we can talk about potential across a membrane. Okay, and we're going to get to that in a minute. When we're moving ahead, there's some key players we need to talk about. You need to memorize all of these. Na is sodium, K is potassium, this is chlorine. When it's minus, when it's a charge, it's a chloride ion. And this stands for organic anions. So most of the cells, proteins, DNA, are a net negative charge. So because we have these inside the cell, that negative charge is going to be inside the cell. So when we look at these are ions. Ions are charged particles. And these are the main ones that we're going to talk about for a little while. Later on down the road, we're going to throw in calcium. Calcium is Ca++, Ca plus 2. These are all monovalent. So valence refers to the charge. So if there's a charge, there's valence to it. Mono means one. Okay, so these are all monovalent. Anything that's a positive charge is a cation. Anything that's a negative charge is an anion. Okay, so sodium is a monovalent cation. Chloride is a monovalent anion. Calcium is a divalent cation. Okay, don't worry too much about those. I'm introducing the terms now. We will be using those words later down the road. All right, so these are kind of the key substances we're going to be talking about for now. As you know, there's lots of different things in your body. So I'm not saying the other things don't do anything and they're not important, but for what we're going to talk about with action potential, these are the ones that we're going to spend the most time focusing on for now. Now, I told you there's a difference between the intracellular and the extracellular fluid. What determines the concentration of ions is a couple things. One is the membrane permeability. So if something can just go right through the membrane, then obviously its distribution is going to be affected by that. When we're talking about membrane permeability too, usually we're not just talking about whether it can go directly through the membrane, whether it's fat soluble. Here we're also including channels. So if it's permeable, so water, I told you about those aquaporins. The aquaporins make the membrane highly permeable to water, and water can essentially freely move into or out of the cell. Other things, we're going to need some energy. Okay, so we're going to talk about transporters and pumps. These aren't channels, so a channel is just a tunnel, and things are going to move passively through those tunnels. They'll move down their concentration gradient. Sometimes, though, we're going to have to move things against their concentration gradient. So if I have a high concentration here and a low concentration here, things aren't just going to move this way. If I have a pump, I can actually pump things against their concentration gradient. Now, the key with transporters and pumps is usually they're going to spend energy. ATP is the currency of energy in the cell. Okay, so all of these things together are going to come into play when we determine the concentration of ions and other substances in the cell. Now again, when I'm talking about ions, I'm talking about sodium, potassium, and chloride for right now. If you look at the concentration, I want you to pay attention to NaCl and K. If you look, the way I remember it basically is salt. Table salt is NaCl. NaCl is on the outside. So in the extracellular fluid, we basically have salt water. In the intracellular fluid, we have less sodium and chloride and more potassium. Okay, so I just remember sodium chloride outside, the other one, potassium, more on the inside, a higher concentration. You don't have to memorize the numbers here, but you do need to know that the concentration of sodium and chloride is greater in the extracellular fluid than it is in the intracellular fluid. Now, how does this happen? How are these concentration gradients established? That we'll talk about in a moment. Here is a cartoon showing our cell membrane. It's a fat sandwich, right? Phospholipid bilayer. We got the extracellular fluid here and the intracellular fluid here. If you look, there's a high concentration of sodium and chloride outside, a lower concentration of potassium outside. On the inside, it's basically the opposite. We have potassium and then low concentration of chloride and sodium ions. Now, I told you about the force of diffusion and the electrostatic pressure. Let's look at potassium. Okay, so potassium's an ion. There's channels, so it can move in and out. It can't just diffuse through. It needs a channel to go through, but it can move. The organic anions, so the DNA and the proteins, are large. Okay, so these can never move. They can't leave the cell. They're always going to be there. These have a net negative charge. Okay, so the inside of the cell, because of all these organic anions, is going to be negatively charged a little bit. So if we look at potassium, which way does it want to go? We'll start with this example where we have a high concentration. Where does it want to go? The force of diffusion, we're going to go from high to low concentration. So that's going to try to drive it out, as this arrow shows. Now this is positively charged. It's attracted to negative charge, right? So the electrostatic pressure is going to drive it inside. Okay, it's going to try to keep it inside. Now, let's just pretend we suddenly get rid of the membrane. It's gone. Is the potassium going to move or not? I've got one force driving it out, right? I've got another force trying to keep it in. In this class, for our purposes, most of the time, the force of diffusion is much, 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 much stronger than electrostatic pressure. Okay, so here, if we suddenly got rid of the membrane, the potassium's going to want to go out. It's going to be driven out by this force of diffusion. Now, to see if you understand, think about potassium on the outside. Which way are the forces going to go? The force of diffusion is going to keep it outside, right? We have a higher concentration inside. Okay, so that's going to try to keep it outside. How about the electrostatic pressure? Positive is going to be attracted to the negative ions on the inside. Okay, so if you followed that logic, you're in good shape. If you didn't, you need to go back and try to understand it again. If that doesn't work, speak to me, please. All right, let's look over at sodium and chloride. Again, we have a higher concentration outside than we do inside. So in both these cases, the force of diffusion is going to drive sodium and chloride into the cell. The electrostatic pressure is also going to drive sodium in because the positive charges are attracted to the negative charges on the inside. Okay, so there's two forces, diffusion and electrostatic pressure, both driving sodium in. Chloride, the force of diffusion is going to be driving it in, but the electrostatic pressure is going to be repelling it. Okay. Now, in this particular situation where I've got sodium chloride on the outside, lower concentration of potassium on the outside, why don't these ions move? Normally, they just don't move because the membrane won't let them. If there's channels open, then they'll move. Okay? But at the resting state, that's not what happens. The ions can't move very well. So they want to, they just can't. All right, here's another diagram, a little more detail that you can kind of work through. In the extracellular fluid, it's slightly positively charged compared to the inside. I have a higher concentration of salt, sodium chloride, on the outside than I do on the inside. There's potassium outside, but the concentration is less. Okay, so if we look and let's say we have ion channels, if we have our negatively charged proteins, our big proteins, they're too big. They're not going to be able to pass very easily, so they're going to stay in the cell. Okay, so those big organic anions don't move. Okay, so you just need to know they're there, but don't worry about their movement. Sodium, chloride, and potassium, you do need to worry about that. All right, so let's look at potassium. Again, we have a higher concentration inside than outside. Diffusion's driving it out. Electrostatic pressure is putting it in. In this particular case, what would happen? The channel's open, so now potassium can flow. Which way would it flow? Diffusion is stronger. Okay, so potassium, we would predict, would leave. Chloride ion. Diffusion, right, higher concentration to lower concentration is pushing it in. The electrostatic pressure, negative, would be repelled, is pushing it out. Again, if we just opened a channel, it turns out that diffusion wins and chloride ion would come into the cell. Finally, sodium, we've got the electrostatic pressure and the force of diffusion both pushing it in. Okay, so if this channel opens, sodium's going to flow into the cell. Now, normally, all these channels are closed. So if the channel's closed, what happens? Nothing, because the ions can't move. Just one more cartoon basically showing you the same thing. Here I do have some numbers. You don't need to memorize the numbers, but I just want you to get an idea. Here we have the extracellular fluid. Okay, so I'm sorry, the intracellular fluid. So if you look, the amount, the concentration of potassium inside the cell is much, much higher than it is outside. It's about 35 times more concentrated inside the cell than outside. Okay, so there's a huge concentration difference. If we look at sodium, it's opposite. It's, something like 10 to 12 times more outside than inside. Chloride, again, about 30 times more concentrated outside than inside. Okay. Now, again, these will move when the channels are open, but if the channels are closed, they can't move. So I'm going to stop in this video right now. This kind of is setting you up with some basic concepts to understand the rest. The basic structure and properties of the cell membrane, right? It's that fat sandwich. It has proteins in it. Those proteins, some of them are channels that are going to allow things to pass through. Because the cell membrane is lipid, and it's not going to allow charged particles like sodium and chloride just to pass through it. It also isn't going to allow big things like proteins to pass through it. A gradient, right? Just where we've got a high concentration in one place, a low concentration in another, and intermediate concentrations in between. And the electrical potential is that separation of charge in space. The cell membrane is going to contribute to establishing and maintaining electrical potentials because it's going to basically keep those ions from being able to move and reach equilibrium. Diffusion and electrostatic force, again, you need to be able to explain those. One thing you hopefully will remember is that this is much stronger. So in the case of neuroscience, talking about neurons, you're going to spend more time thinking about the force of diffusion than the electrostatic force. Okay, for our purposes, we're going to largely ignore this, but I want you to know it exists. Right, so hopefully that'll help get you started. Make sure you understand these before you move on to the next video where I'm going to talk about the resting membrane potential.